Welcome back for a continuation of our riveting discussion on the fun, emphasis on fundamental theorem of calculus, part one, right? This is a huge discovery. We've got an expression up top that tells us, wow, this theorem says that all continuous functions have antiderivatives and that there's a huge connection between antidifferentiation and differentiation. The two operations are inverses of one another. So we're looking at 5 and 6 now. We're trying to make sure this is of the form that we just be able to use that canceling effect. And this theorem says you've got the integral, definite integral from a constant to the variable expression x. So here I've got the opposite. 5 is another one where I'll have to do a little switcheroo here. We can switch the limits of integration, put the 10 at the bottom as the lower bound, x as the upper bound, as long as we change the sign of our solution. And then I'll just recopy what looks like the function f of theta, right? We'll say tangent of theta with respect to theta. So now this is looking better. I'm finding a derivative of an integral. So I can keep the negative sign in my answer and use that canceling effect to just have this function evaluated at x. So this will be negative tangent of x, derivative of an antiderivative. And then closing off this section, number 6. 6 looks like it's set up nicely with a continuous function, and you've got 1 here, a constant on the bottom, but you have a more interesting expression than just x, and we saw this back in number 3. We'll have to apply the chain rule. We'll just keep that in mind when we are taking a derivative. Plugging in the x squared is really what's going to happen, but we'll get to that when we get to it. We want to take h prime of x, a derivative of what's already here as an antiderivative, as an integral. So I'm going to take this variable expression and just take the expression I see here and plug it in everywhere I see r. So you'll have the square root of 1 plus x squared cubed. Okay, that's part 1. We know this one's going to involve a chain rule because it wasn't just x sitting up there. It's something more interesting than just x. So if you could tag on by the chain rule, it's derivative, the derivative of x squared, which is going to be a 2x. And that's pretty much how your answer will look. H prime of x, the derivative, will be 2x times this square root expression, 1 plus x to the 6th. Okay, looking good. You've got some practice underneath. These would all, 6 of these, would be really good to do on your own, to pause the video and give them a try, using what we did above, right? Using the examples above as a guide. I feel like you'll find something similar to each one of these down below. I would love for you to pause the video. At the very least, can you knock out 7, 8, and 9? Because those look completely straightforward. Each one of them has a nice constant in the bottom, and it's got a variable, a nice x or a y or an x in the third one sitting up top. So pause, at least try 7, 8, and 9. If you feel like you're getting the hang of it and you want to make some guesses and look ahead at 10, 11, and 12 too, do those while you pause. But I'm going to do the same. I'm going to pause, do at least the first 3, and then join you on the ones where we would need chain rule. So I'm going to time out. Now I will time back in, and if you don't mind checking these, that would be great. And you may have looked ahead, so I might need to play a little bit of catch up. So 7, 8, and 9, very straightforward in general. It's of the format where I can just plug the variable in for the t that I see originally in the problem. What about 10? 10 might have a chain rule, a little bit of chain rule action going on, because it doesn't say the integral from 2 to x. It says the integral from 2 to something more interesting, the 1 over x. So keep a chain rule in mind. And let's give this a try. We need to find h prime of x if we haven't already. And then we can, first things first, we can evaluate, right, arctangent of t at this variable expression. So everywhere we see a t, we get to plug into this original expression, arctan of 1 over x. That would be step 1. I'll throw that in parentheses. Step 2 is we keep in mind that this itself has its own interesting derivative, right? 1 over x is just like saying x to the negative 1. And I can power rule this. I can swing down the negative 1, take a derivative, bring it to 1 power lower. And then I'll just combine this to get a final answer, right? The derivative of the original expression will be negative arctangent of 1 over x. How about we swing the x squared to the bottom of the fraction, right? Because it's to a negative 2, so divided by x squared. Okay. Last but not least, let's look at 11 and 12, right? Again, you could just try these on your own and check them with my answers. Again, I'm thinking chain rule for this one. It looks very, very similar, right? A square root of x just like we had up in one of these, up in number 3. So we'll go down, and I see the constant nicely at the bottom. No need to change limits of integration here. We can call y prime the rate of change of y. Let's say we're reversing integration, so we're just using the original expression first, evaluated at the square root of x, and then not forget that we have a derivative to tag on, the derivative of the inside. So we'll use, what do we use? 1/2 x to the negative 1/2. And then take your time with the algebra here. This can be simplified too, just so your answer looks a little bit nicer. I think I'll be left with just a cosine of the square root of x up top of this answer. And on the bottom, you've got the 2 that I see here. You've got the square root of x that was already here. And how about another square root of x down in the bottom to join it? So this would probably look better as cosine of the square root of x over 2x. And I think we can call it on that one. Whoops. All right, and then the last one on the page. My variable expression needs to be the upper limit of integration. So first things first, let's switch the sign of this expression, and that will entitle us to switch the limits of integration. So we can make it negative. We've got variable expression up top, and we've got the constant number at the bottom. I don't see any problems with continuity, so we'll go u cubed over 1 plus u squared. And now I think it's ready to apply the fundamental theorem. Let's say that the derivative of the antiderivative is going to be this expression for starters with this guy plugged in. So it'll be y prime. So 1 minus 3x to the third, and then on the bottom, 1 plus. Now I have to put in the 1 minus 3x for the u on the bottom. That is squared. Did I forget anything? Well, it doesn't just say x up top. It says something that has a derivative that's not just 1. So chain rule. Let's apply chain rule and take an inside derivative that should just be the constant -3. And again, you'll see it just cleaned up with the -3 up top. So -3, this thing to the third, 1 minus 3x to the third, and then you've got that. I'm just going to leave this expression, 1 plus 1 minus 3x squared. Okay. So the rest is up to you, right? I want you to get a little bit of a chance to practice with this. All of the examples you see on the next page are great, so take your time with them. I was just looking around to see if anything would be a little bit out of the ordinary. I think I see nice setups with constants on the bottom and a variable x up top for 13 all the way through 18. So I'm liking the looks of those. And then a little bit of finagling you have to do with the bottom ones. And 19 and 20 just look a bit different from the others that we saw on the other page. 21, 22, the ones below, I think we can apply chain rule for. But can we just take a look at one of your homework questions before we go? Just look at 19 together. Because we haven't seen an example yet that's a definite integral, which is a variable expression to another variable expression. Both of your limits of integration in both of these are in terms of x. I want to draw a picture that can help us with this setup because I would love to split this thing up into 2 parts that would have just a constant as your lower limit of integration and a variable expression as your upper. It makes this one a little bit tougher. Think about a simpler example. Let's say I have some kind of curve, right? I'll call it f of x. Maybe, I'll just call this one f of x. And I'm going to say I want the integral from some number to another number that's 2 above it. I mean, that's what this one says. You're going from the number x to 2 above x. So I'll pick my favorite number. I'll pick 7, and 2 above that is 9. So I'm interested in this integral here. But I'd like to write that, I'd like to use 0 to be able to write this definite integral, where I could say the integral from 7 to 9 of f of x with respect to x can be split up. Couldn't I take the whole entire integral from 0 all the way to 9? So that would be this distance in red, so the entire area under the curve here from 0 to 9. And then maybe just subtract a little chunk of that area, right? If I'm only interested in this blue shaded area, let's take the whole red shaded area and subtract, I guess I need another color, subtract the green. Because I think that could get us just the blue, just what we wanted. So I'm subtracting the integral from 0 to 7. I just really like this format because it gets us set up with a nice 0 on the bottom and possibly a number 19, a variable expression up top. So I consider these two a lot trickier. I'm going to split them for starters into 2 separate definite integrals. So I'm going to go integral of the whole thing from 0 to the upper limit. So 0 to x plus 2, the variable expression, expression of 4t plus 1 with respect to t, minus, right, kind of like in the format I put here, minus the integral that's just solely from 0 to x, okay, of 4t plus 1 with respect to t. So I'll give you the disclaimer here that this problem isn't going to be this tough for very long. Even as soon as tomorrow, we're going to have a quicker way to be able to evaluate this. But this is one way to get a good setup that'll look like what you need for Fundamental Theorem Part 1. So I guess now's the time to take a derivative, right, of these two separate definite integrals. So let's apply the theorem. Let's say, okay, constant, something that's continuous up to a variable expression. So we can take a derivative of an integral, meaning those two operations cancel, and we can just plug into the expression we see there, an x plus 2, right, everywhere we see t. Generally, I'd also think, well, this is more than just x, it's an x plus 2. Should I be tagging on an inside derivative using the chain rule, put this in parentheses? Not really necessary here because the derivative of x plus 2, we get kind of lucky, it's just 1. So here's the first part of it. Now that this second part's set up to look like Fundamental Theorem Part 1, we can do the same thing with just x. So maybe I should be careful and put this whole thing in parentheses, but I'll go 4x plus 1. Now I wonder, this is your answer. It's not very simplified, but I wonder if our answer could get real simple here since this time we're integrating from a variable to a variable. So let's see, f prime of x, you've got 4x plus 8, and then not for long with the 4x because minus 4x, and we're going to say minus 1. 4x's are additive inverses here, plus and minus. The 1's are additive inverses here. Later, when we get a quicker way to evaluate what you see here, we'll even arrive at that answer sooner. You're just going to get the constant 8. So 1920, a little out of the ordinary tougher. You got some easy ones up top. You got some more thought-provoking ones at the bottom. Don't have too much fun with this homework. Enjoy the rest of your day and hope it's refreshing. Talk to you later.